Alright, we're back. So I was just noticing on the break that someone on Twitter was commenting that they were having trouble watching on Twitch with a bunch of, they have like a lot of JavaScript disabled in their browser. So there's actually a command line tool you can use to watch Twitch streams and other streams without having to load them in your browser, called Live Streamer. Yeah, livestreamer.io. And you just give it the URL of your page, or of the Twitch stream you want to watch, and it'll find the URL of the video stream and open it in VLC or some other local video player. So that's an option for people that have a lot of tight browser security. Alright, so back to our project. So we have our these disks represent coins, and when we move the mouse onto one, it starts to flip over in some direction. And the direction is based on the direction that the mouse comes in on. So our next step is we want to actually update the coins that are flipping and allow the mouse to continue to push them over, I guess, until they get to the point where they're completely at the edge, and then they'll just kind of animate down on their own from there. So, let's see, how are we going to do that? Here's our update function, and we get the mouse, and we are currently processing all the flat coins to figure out which ones need to start flipping, and which ones are going to stay flat. So then we also need to do processing with our flipping coins. And let's see, the interesting part here is it'll maybe be harder to do the collision detection because we have these ellipses that are kind of rotated in different ways. So I'm thinking it might be simplest to just process all of the flipping coins and pass in the mouse position for every one of them. And let's see, it shouldn't be too big of a performance hit because there are going to be very few coins flipping at the same time because the mouse can only be in one place at a time. So I think we'll plan on doing that, and the first part we'll need to do is to write a function to handle the touching of a flipping coin. So we'll call it maybe push flipping coin. That's going to take a point, which is the mouse location, and a flipping coin, and give back a new flipping coin. So we have the mouse position, we have the coin. So let's see, what do we want to do? So again, in here, the circle is representing the arc that the edge of the coin will trace as it flips over, and this line segment here is where the coin is, if we're imagining looking from the side. So if the mouse is coming in, I guess we want to imagine that the mouse is pushing this edge, and we want to kind of push it over the flip point, or the anchor point. So what do we want to do? I guess if we're imagining from the top, let me pull this up. So in this case, I started flipping the coin this way. And I guess if we're inside of the coin, then we want to, I guess, calculate the distance between the line that we're flipping over and where the mouse is. So let's see. I guess the best way to do that is to kind of rotate the mouse vector, or find the direction. No, find the vector of the mouse relative to the anchor point. Then rotate that by the orientation, and then we can just take the y component of that vector. So let's see if that's going to work out. And then I guess once we have that y vector, we can then, I guess, calculate the inverse cosine to figure out what the flip angle should be at that particular point. Okay, well, I guess let's try writing this. And I'm most definitely going to get the orientation direction wrong probably, but let's see how we do. So we're basically going to take our coin, and we want to change one thing. We're not changing the radius or the anchor or the direction or anything like that. All we're changing is the flip angle. And that, we said, is going to equal a whole bunch of stuff. So I guess let's start building this out from the beginning. So first we want to take the mouse position vector, and we want to subtract the coin anchor point. So that'll give us a vector that points from the anchor point. Let me pull this back up. That points from the anchor point here to wherever the mouse is. Then we want to rotate that vector so that this, for instance, this line along the front of the coin, we want to rotate that to be horizontal. And then we'll have actually the linear distance. I'm not sure the correct word for that. But like if I move the mouse kind of horizontally relative to this tilted line, then that shouldn't cancel, or that shouldn't change anything. It's just the distance in the direction perpendicular to the orientation that we care about. So I think to do that, I want to rotate, and let's see. So what is rotate in vector math? That is multiplying by the normalized vector, right? So if we multiply by the normalized, what do we have? We have the center direction. So the center direction is a vector that points from the anchor toward the center. Yeah, okay. I think maybe we should look up a little bit of vector math, because really we want to essentially use that center direction as our x-axis and figure out how far along that axis a particular point is. And that's maybe just something like the cross product or something. Vector distance in coordinate system of another vector. Not even sure the right thing to search for in those terms. Vector distance to line. Point line distance. Distance from a point to a line. How to calculate the shortest 2D distance between a point and a line. Okay, so that's what we want. vectors, distance from a point to a line. And this is talking about line segments, not a line. Okay. Vector normalizing coordinates. Normalized vector, normalizing a vector. Yeah, okay. I don't even know enough to know what to search for here. So let's try to just do this in steps. Excuse me then. So if we multiply this by the center direction and normalize that, then that should be the same as rotating. Coin.center direction. Okay, and then let's debug.log this. And let's put this in a let block for the moment. We're just going to print that, and for the moment return our same coin. And this is just called sub. And is there a multiply in here? I guess it's just one of these products. Direction, scale, negate. Where is it in here? Distance squared, no. Direction, no. Normalize. Scale. I was expecting another function that took two vectors and gave a third one back. How to rotate a 2D vector. Oh, I see. I guess the cross product is perpendicular. Okay. So I thought that would be a lot more straightforward, but I guess I was misunderstanding how this would work with vector math. So let's see. Let's just think through this again and make sure we're heading the right direction. So I want basically to calculate the distance from the mouse to this particular line, essentially. I guess we could do a shortcut for now and just actually calculate the distance. Let's try that out as a simpler math and see what happens. So we'll take the distance from mouse position to the anchor point and just print that out. And we first need to actually call that. So here we're going to have still flipping equals list.map of, what did we call this function? We called it push flipping coin with the flipping coins. And we will append those now. And we also need to pass the mouse position here. Okay. So back to Chrome. Let's bring up our console. And, okay, so we're getting distance. It's shrinking as we get close. If we get over here, I guess we'll see how this feels when we actually interact with it. But it seems to be getting the right distance. So then, what we also want to do is now take the arc cosine, I think, of that, except we want to normalize this based on the radius. So I guess we want to divide this by 2 times the radius. We want to divide by the whole diameter. Coin.radius. And then take the arc cosine. Okay. Let's see how that goes. And ElmReactor is getting slow all of a sudden. Looks like my network might have dropped off for a minute. Okay, let's see if that comes back. And, alright, so here we are trying this out. And the angle, okay, the angle is getting larger and larger. And it should get to half of pi, I guess, as we get there. Okay, that seems roughly correct. So I think we're ready to plug this in and see how it works. So we're going to take the coin and change the flip angle to this value that we're calculating by taking the distance, dividing it by the radius, or excuse me, by the diameter, and then taking the arc cosine, and that should tell us what angle we're flipping at. Yeah, okay. So there's definitely some issues if I move the mouse too far out. And yeah, okay. We can pull it up and great. Okay, so we have a couple edge cases to handle. One is when I pull it back too far. I guess that's when the arc cosine is not a number, in which case it's when the distance, I guess I'll call this d, so this will be the arc cosine of d. D equals that, and we'll also say if d is greater than or equal to 1, then we're going to just return the coin. Otherwise, we will update it. Okay, so that should fix that first problem. Great, where we can't break it by pulling back too far anymore. Then our other problem is when we go over the top. So I guess now we need to think about how we're going to model this. So once we get close to the top, we want it to just start going by itself, I guess, for the rest of things. And I guess I'm debating whether we should have this represented as a flipping coin, or if we just need to have a third type called like falling coin or something like that. And I think maybe having a falling coin would be good. I mean, we'd certainly have the type safety here. Let's see. The downside, what would be the downside? I guess we'd kind of have some duplication in here, but we're also never calling start flip or push flipping coin with one of the falling coins. So yeah, I think we should just have a new type called falling coin. And this will be called the fall angle. And let's see how this goes. This might be the wrong modeling choice, but we can at least learn from our mistakes if it is a mistake, and learn from our success if it is a success. So this means we're going to have a couple different options here. So this flipping coin could turn into different things. It could continue to be a flipping coin. It could be flat, in this case, actually here. Or it could turn into a falling coin. So I guess this is where we have a new type. I guess let's just call it push result, because it's kind of specific to this pushing function right now. So we may have a stop, in which case we'll get a flat coin out. Or we may have a continue, which will get a new flipping coin. Or we'll get a flipped, in which case we'll get a falling coin. So we'll get one of those from here. So in the case we just handled, we are saying that, let's see, we're saying that we are getting a continue with that. Then in the case where d is greater than 1, we're going to have a stopped, and we're going to convert this back into a flat coin, in which case our center equals add of the coin.anchor plus the coin.center direction times the radius. Scale coin.radius. And then we also have the radius equal to coin.radius. Okay. And then down here, we're going to need to destructure this. So I think we're going to have 3 lists. We're going to have the stopped flipping, the still flipping, and the flipped. And I guess we'll build these up using a fold. And we'll have a function in here, which will get the coin. And then we'll do the case push flipping coin of, and if we get a stop, then we are going to add it. So we're basically going to fold over a tuple of 3 lists with each of our flipping coins. And call this, and depending on which result we get, we will stick it into a different list. So let's see, we have stopped, still, and flipped. So then here, if it's stopped, we're going to add the flat coin to that. If we get a continue, we are going to add that coin to the still flipping. And if we get a flipped, we are going to add that to our flipped list. Okay, so then we get all of those. Then we need to add here our stopped flipping coins. And then we're also going to have falling coins, which we're going to add. And this will be our new falling coins, or the flipped ones, appended to the ones that are already falling. Okay. Then our model type needs to be changed here. So we now have falling coins, which is a list of falling coin. And when we start out, our falling coins is an empty list. And I guess that's good for now. Okay, so the one thing we should see now is if we start this and then pull back, it should turn yellow again when it becomes a flat coin. Great, so that works. So we can pull back at any point and set it up. Okay, the other thing I'm seeing is there's a bit of a flash when we start, and that's because when we first start flipping the coin, we are immediately setting the flip angle to be 45 degrees. And I think we really should set it to the same value that the push flipping coin sets it to, which should be, well, maybe we can just set it to 0 and let the next frame do it. Let's see how that looks. Yeah, okay, that actually looks fine. And I kind of feel like bumping up the size of this coin a bit more too. Let's make this like 65. Yeah, okay, so we can push it from any direction. So our last step is when we get close to pushing it over, we want to actually move it to the flipped coins, or we want to move it to the falling coin state. So that I think will go here. We'll say else if D is less than or equal to like 0.01 or something. So I want to have a little bit of leeway so we don't have to exactly push it all the way to the edge. Then we will have flipped, and in this case we will make our falling coin, which is going to have anchor equal to coin.anchor. the radius, of course, will be coin.radius. The center direction will also be the current center direction, and our fall angle is going to be 90 degrees, I guess. All right. So now, when we get it to the edge, it should just disappear because we're not rendering the falling coins at the moment. Oh, there it is. Okay. Cool. So let me stick this back in the other window. Then we need to render our falling coins. So I guess we'll follow the same pattern we have here, just with the falling coins, and we will call render falling coin. Which is actually going to be almost the same as this. So maybe there's a refactoring in here, or possibly it was a bad choice to make this a separate type. But in any case, let's see what we can do here. And I'm going to make this be just kind of like a purple color for the moment. So we should see that, and this is render falling coin, and this takes a falling coin. And then here we have the fall angle. Okay. And I guess we're not even going to see anything, because right now this is 90 degrees, which means it's going to show nothing. So I think we need also our update function to update the falling coins. And there's two options that can come out of that. It can either be continuing to fall, or it can have landed flat. So we will have finished falling coins, and we will also have the still falling coins. And we'll do the same kind of fold that we had here. We're going to advance falling coin, I guess, is our function. We have no position to pass. And we'll pass coin. And we're only going to have two lists. And I think we'll just use the result type for this. So we're going to have, it'll return either an OK with a still falling coin, or an error with a flat coin. And we'll start with two lists. And we need to write advance falling coin, and this is falling coins. And then finally we'll need to stick these together. So this is the still falling coins. And then the flat coins also need to get added to with the finished falling coins. Okay, so now all we need to do is write this function, advance falling coin. I guess we'll put this here, and we said it's going to take a falling coin and give back a result, which will either be a flat coin if it's done, or a falling coin if it's not done falling. Okay. And how should this work? I guess let's for the moment just linearly increase the fall angle until it gets flat. And we we might want to do something more sophisticated with like have it accelerate so it kind of falls more naturally. But let's see how just a linear fall looks. So for the moment, we are going to just return the coin and say that the fall angle equals fall angle, the old fall angle, plus 1 degree. Let's see if I can spell degrees. And we're going to return OK with that. All right, so let's see what happens. Okay, that sort of works. There's one problem, which is that we want that to happen not when the mouse moves, but when the animation timer fires. So let's import animation frame. And I think we'll need to install that as well. ElmLive animation frame. And start up the reactor again. Then we will subscribe here to now a batch, since we have two things. So we'll subscribe to our mouse moves, and we'll also subscribe to animation frame dot times. I guess it doesn't matter because I'm not actually going to bother looking at the value. I'm just going to animate every time there's a new frame. So it could potentially, like the animation speed will change if the frame rate changes, but for this demo, I'm totally fine with that. Okay, so where's our message type? And yeah, this file is definitely getting big, so we should totally refactor this in a few minutes. All right, and now we need to handle the new tick message in here. And if we get one, let's see, we want to just take this finished falling, still falling part. That is going to go in here. And then we'll be returning our model with no command. And we will be changing the falling coins. Let's see. So when we move the mouse, we may get new falling coins. And we'll add those to the existing falling coins. Then here, falling coins will equal the still falling coins. And the flat coins is going to equal the finished falling coins plus the starting flat coins. And what else is up here? Ah, yes, the finished falling we aren't calculating up there, so that can just get left off. Okay, so let's try this out. So I'm pushing it when it's orange, and then if I push it over the edge, it becomes a falling coin. Okay, and currently we're never stopping the falling animation. And another optimization I'm realizing we can do is we only need to run the animation times if there are actually any falling coins. So we can use the model in our subscriptions, and we'll say if model.fallingCoins equals the empty list, then we need a sub.none here, otherwise we'll subscribe to the animation frame. So that way, there aren't extra events being fired or messages being created when there's no animations that are actually playing. Okay, and I am going to increase the threshold here for our flipping coin. Make this like maybe 0.03. Oh, I see. Okay, and again, that's actually a problem with this cheat we're doing of just finding the distance rather than finding the distance in one direction. Okay, so our next step here is to make these falling coins stop at a certain point. So I think we just need to calculate the new angle, and we'll say if the new angle is greater than or equal to 180, then we're going to make a flat coin. Otherwise, we will make our continually falling coin. And our flat coin, we have the radius, which is easy. We just copy it over. And then we also need the center, which we're going to need to calculate. Let's see. So now the center is on the opposite side. So this is going to be similar to when we stopped the flipping coins, except that we're moving it in the other direction, because now we flipped it over. So let's just try this and see it go wrong, first of all. So if I push it, now it'll fall, and then... Oh, whoops. This needs to be 180 degrees, not 180 radians. Okay, so we can push it over, and then it resets to where it used to be. So what we actually need to do is negate the center direction. Ooh, and I guess we can do that just by negating the radius. Is that right? Let's see. Yeah, cool. So we can push the coin over, and when it lands, it calculates its new correct center position, and then we can push it in a new direction. Awesome. Okay. So let's see. So what do we want to do next? I guess there are a few things. One is this distance calculation for pushing the coin is really kind of hard to use here. Because if I'm like over to the side, it stops flipping, I guess. Let's see. Actually, can we use the dot product for that? What is the interpretation of the dot product? Distributive law for the dot product. Oh, that doesn't help. Dot product. Rotate to baseline. Ooh, okay. I think this is actually what we want, probably. So the dot product of two things... Yeah, okay. I'm having trouble kind of explaining this in words. So if we have two vectors, let's see. I'm trying to find a good visual explanation for this. Yeah, the dot product is a scalar, and it is the component of B along the direction of A. Yeah, so what we originally wanted was to to find not the distance between these 2 points, but we want to find the value, or like how far in the center direction is the mouse position. So I think this might just be dot of coin dot center direction. Although I guess we're going to have to normalize these a bit. Oh, hey St. Pal, welcome to the chat. Let's see, you're a beginner programmer. So are you a beginner with Elm, or are you a beginner with for all programming languages? And let's see. Yeah, so one of my earlier episodes, I think actually one of my first ones, was a lights out game that was a lot more straightforward. So this is one that you might be interested in taking a look at. Let me post that in the chat. And there's also one of the other ones that I think was much simpler to follow along with, was the one about the Tangram logo. Let's see, where was that? Yeah, this one. The Casual Saturday Tangram logo. So that's a relatively short one too. Cool. Yeah, I used to do some videos for Java programming for game stuff as well. But yeah, there aren't a ton of people doing game development with Elm at the moment. I've been experimenting a lot with it this month, so there's not a ton of stuff out there. Most of the Elm stuff is more for web app development than games. Although there are a few good examples, but there's not a lot of learning material out there yet. Okay, so let's try to figure out this calculation. So if my mouse is here, and we have a vector which represents the direction from the anchor point to the center, so I guess we want to take the mouse position and subtract the anchor position, and then we'll have a vector for the mouse that's relative to the anchor point. And then from that, we can use the dot product to figure out the component in the direction of the center of where the mouse is. So let's try this. So we're going to sub the coin.anchor from the mouse position. Then we're going to dot product that with the center direction. Then we're going to divide by the radius. And all right, let's see if this works. Okay, nope. And let's see, first thing I'm going to check is if I just got the order of these wrong for the subtraction. Ooh, yeah, okay, this seems to be working because I can move the mouse along this line and it doesn't matter. And I can cross right there and flip it over. Yeah, cool. Okay. I feel like that was mostly trial and error more than anything, but we made it through the vector math. And I guess the other thing we can try to do is well, okay, I'm not really sure that's going to be worth it. I was going to say if the mouse moves outside of where the circle is, then we could just have it cancel and fall back down. Great. So let's see. So what's next? I guess the main thing I want to do is just add some more coins to start out on the board. So I guess maybe we can start with an empty list and use a random generator to create some random flat coins and place them out. Oh yeah, and the other thing I totally wanted to do is refactor here. So let's do a few things. I think there's a coin module that we should be building. So we'll call that coin.elm. This will have stuff related to the data for our coins, which will be these data types. Then it's also going to be these functions, start flip, the push flipping coin, and advance falling coin. And let's see, what do we need to import? I'll just copy all of this over and delete what we don't need. Okay, and then this is the coin module. Then we're going to import coin, exposing all that stuff. Let's see, what else can we pull out? I was thinking maybe these two functions can go in a little helper function. Let's see, what happens if the mouse leaves from the same direction? I think we handled that earlier. It just goes back to being a flat coin. So let's take these two and put these in maybe an SVG slash util module. And point here, this is actually going to be a vec2, which we import from math.vector2. Okay. Then we need to import that. Import svg.util, exposing that. Okay. And then I'm thinking maybe these render functions can also be put in another module. I'm not entirely sure what the best way to organize that is. Because I don't really like the pattern of having like a separate view and model module for each data type. Because really this rendering is more specific to our application than to the data type of coin. But I do think these need to be put somewhere. Yeah, I guess I'm not completely sure. I guess let's just leave it in here for now. Okay, so we'll leave the rest of that in here for now, but we have pulled out two modules, a helper, some helper functions for SVG, and our coin data functions, and all the math that manipulates them. Okay, so here's our initial model. I want to start with that being empty. Oh yeah, and actually one other thing I want to do is make this kind of fit the window size. So like if we keep pushing this coin to the right, it's going to go out of the canvas eventually. Yeah, right there. So I'd like to make the canvas resize itself to match the window. So let's do that first. we are going to need to elm package install elmlang/window. And we'll have in our model window size, which will be a window.size, and we'll import window. Then window size, I guess we can start it at 0, 0. And it just won't render anything. Oh, I guess this is actually a record, which is width equals 0, height equals 0. And I guess that'll be fine, because we'll just show a 0 by 0 canvas until we get a window size. Then, window resized, we'll get a window.size, and we will handle that in our update function. Window resized, and that will simply return our model with our window size changed to the new size and no commands. Then we're also going to subscribe to window.resizes with our window size message. We called it window resized message. And then we also need to create an initial command to request the window size, because the resizes subscription doesn't fire at the beginning of the app run. So we'll say window.size, which gives us a task, and then we can task.perform that with the window resized message. And we need to import task. Okay, so that all works. So let's refresh this. Oh, and I need to restart Elm Reactor. Then let's try moving this over. Still didn't work. Oh right, we aren't actually using that when we render. So let's fix that up. In our view, this is going to be toString of window of model.windowsize.width, and same thing here but with height, and then same thing here except we need to interpolate this. And also here. Okay, so that should do it for that. Let's try flipping these over. And great, we can walk it all the way to the edge of the window now. And we can even resize the window and let it go off the screen. Okay, cool. So then the other thing we want to do is also fire off an event to generate random circles. But I'd like us to know the window size before we fire that off. So I think I'll fire that off from the update here. And we'll say if list.length of model.flatCoins plus list.length of model.flippingCoins plus list.length of model. What is it called? Falling coins. So if all of that equals 0, then we need to generate some coins. Otherwise, we'll do command.none. So in here, we'll do random.generate, and we'll need to fill in some stuff. Okay, so we'll have a new coins message, and we're going to generate a list of random coins. And I guess we should generate what? how many? I guess we should generate some based on how much area of the screen there is. Like if we have 500 by 750, like proportional to the area, we could generate a different number of coins. We want to generate maybe 10 coins for that. So every 30,000 square pixels will generate 1 coin. I guess we want to have a minimum. Alright, let's deal with that in a little bit. Let's just put 20 for the moment. And I think we're also going to need to pass the model.window size into this generator because I want to generate coins that are located on the screen. Okay, so we're going to need to create random coins, which will be a random generator of flat coins. And it also first takes a window.size. So we'll have width and height that we can pull out of that. And then we're going to do random.map2 flat coin, because I think flat coin took 2 arguments, right? Let's see, that's in our other file. Yeah, it takes a center point and a radius. So our center point is going to be a random.map2 of a vector, and we will get a random float between 0 and width, and a random float between 0 and height. And then our second argument will be the radius, which will be a random float between 5 and the min of width and height divided by 2. Okay, and then we need to import random. Then what issues do we have? This is random.list. Okay, and what's our last error? Cannot find the new coins message. Great, so we need to create that, new coins, and that'll get a list of flat coins. And then we need to handle that. Second argument to float is causing a mismatch. I see. Width and height, we need to call toFloat on both of those. And I guess the same thing here. Okay, and then we finally need to handle our new coins message. And in that case, we will return our model, and we'll change flat coins to be the new coins. And I'd also like to remove the other coins as well. So we'll say flipping coins equals empty list, and falling coins equals the empty list as well. Alright, let's try it out. Well, we did not generate any random coins. So what is going on here? I guess let's check our debugger. So we got our window resized. And then at that point we should have generated this message. I see. we had some coins already, so we didn't generate. And that's because we need to delete this from our initial model. All right, and now everything should work. Well, we got a bunch of coins on here. The radius is tiny, and the centers are all at 0. Okay, so something went wrong with our generation. To float of width and height. Ah, okay. Because we're passing the current window size, and we want to actually pass the new size in here, because that's what actually has the window size in it. Ooh. Okay, those are working, but I would say they're a bit large. Let's maybe have the maximum size 0.2 of the width and height. Yeah, cool. That actually looks pretty good. And maybe if we shrink the window up some more. Yeah, cool. So I think that's about all the time I have for today. I think we've noted a few improvements, like specifically if I'm pushing one and the mouse goes way out of bounds, we should stop that pushing. But also I think it would be nice to kind of let it fall back to the ground with an animation. And I'm also realizing that I think it would be nice to have like some momentum to the coins. So like if I start pushing it, it'll actually have some momentum, and if I pull back, it won't immediately follow the mouse, but it would kind of follow itself over. And then also adding some kind of acceleration to the falling speed. And I think in particular it's kind of bad because we're incrementing the fall angle linearly, whereas it would probably look better if we incremented like the kind of the linear distance that the edge has to fall linearly rather than the angle. Actually, maybe let's try speeding this up real quick. The advanced falling coin. Okay, let's have this maybe fall 3 times faster. Maybe that'll give it a better feel, first of all. Yeah, okay, that actually feels a bit better. Cool. But yeah, I think there are definitely some improvements that could be made for this. So I might take a look at that in the future, although I do have plenty of project ideas lined up for December. So thanks for tuning in today. And yeah, remember to find an important issue in politics this week that you're concerned about and give your representatives a call if you live in the United States, and start getting more involved in the political side of things. So thanks for checking out ElmLive today, and let me know if you're working on any cool Elm projects, and I will see y'all next time, or in the next couple days if you are tuning in to any of the few remaining Codevember streams. So thanks, and have a great weekend. Bye.